Hey, it's me, it's your pocket tutor. And today, as I said last time, we're gonna do some exercises on vectors and forces, just to see how to use them and to understand what are the forces that we talked about last time. So, first of all, this exercise asks, which drawing represents the sum of f1 plus f2? Now, f1 and f2 are these two vectors. And if you remember, we talked about the sum and difference of vectors. And we have two different methods that are head to tail and the parallelogram method. We can use either one of the two. In this case, the parallelogram method is much easier since the tail of the two vectors coincide. Let's look at the first one. We see that the two heads of the vectors are pointing in this direction, respectively. So the vector, the sum vector, must be inside this area. This means that this one is wrong. Let's look at the second one. Well, when we draw the parallelogram in this case, we can see that the head of the sum vector, the green one, doesn't lay on the vertex of the parallelogram. So also this one is wrong. While the last one, when we draw the parallelogram, we see that the head of the sum vector coincides with the vertex of the parallelogram. So this one is the right one. Very easy. The second exercise says, on Mars, the gravitational acceleration constant is g equal to 3.74 Newton over kilograms. We saw in the last lesson that the Earth gravitational acceleration constant is equal to 9.81 meter over second to the second power. Now you will ask why the Mars one has a different unit of measurement. Well, actually these two units of measurement are the same one, because if we look how to express the Newton with the international system, we'll see that Newton is meter over second to the second power times kilograms. If we try to see what happens when we divide Newton by kilograms, we see that this one is exactly meter over second to the second power. The two units of measurement are actually the same. The exercise then asks, how much does a sugar pack of 1 kilogram weigh? We saw that the equation to compute the weight of body is given by F, or also weight, is equal to the mass times the acceleration constant. Therefore, this one is equal to 1 kilogram times 3.74 Newton over kilograms. And this is equal to 3.74 newtons. Easy. The next one says, on the moon, the force weight is 6 times smaller than on the Earth. How much is the value of g on the moon? What does it mean? It means that if we have a body that has a certain weight on Earth, on the moon, this body would weigh 1/6. And how to solve this one? Well, let's write the equation to compute the weight. And this one is F is equal to m times g. And if we consider it on the Earth, this is F on the Earth is equal to mass times g of Earth. While F, the weight on the moon, is equal to the same mass times g on the moon. Now it says that the force weight, that are these two, on the moon, so this one, is 6 times smaller than on Earth. So we can write that the force on the moon is equal to 1/6 of the one on Earth. And therefore this is equal to m times g on the moon and is equal to 1/6 m times g on Earth. And this is what we were looking for. So if we consider this equation here, this one says that m times g on the moon is equal to 1/6 m g on Earth. We can then simplify the mass, and this leads to g on the moon, that is what we're looking for, is equal to 1/6 g on Earth. We know the value of g on Earth, that is 9.81 meter over second to the second power. Therefore, g on the moon is equal to 9.81 over 6 meter over second to the second power. And this one is equal to 1.635 meter over second to the second power. Let's now see an exercise on the friction. This one says, the static friction coefficient between a 56 kilograms wooden box and the floor is 0.27. Remember that the friction coefficient doesn't have a unit of measurement. It's just a real number. And then it asks, what is the value of the minimum force required to put the box in motion? Well, let's draw a sketch. We have a floor, we have our wooden box, and we know its mass. So let's assume that we are pulling the box from this side with a force F. In order to put the box in motion, we need to apply on it a force that is equal or greater than the friction. And in this case, we have the static friction since the box is still. We've seen the equation to compute the friction, and this is Fs for static is equal to mu s times n. Now mu s is 0.27. We need to find what's n. I told you that n is the normal force. Is the force that a surface applies on a body in order to keep the equilibrium along the perpendicular direction with respect to the surface. Now, in this case, the perpendicular direction is this one. And the acting forces along this direction are, first of all, the weight of the body itself and the normal force, n. Now, the value of n is the same of the weight because we need equilibrium along this direction. The normal force cannot be lower, otherwise the body will start going down, but it cannot do so because otherwise it would break the surface. And in the same way, the normal force cannot be greater than the weight, otherwise the box, in this case, will start floating in the air. And therefore we can write that n is equal to weight, that is equal to the mass times g. Now we're thinking that we are on Earth, so g is 9.81, and this means that the normal force and the weight are equal to 56 times 9.81. And this is equal to 549.36 newtons. And now we can compute the friction. So the static friction is equal to 0.27 times 549.36 newtons. And this is equal to 148 times 3.272 newtons. Next one. This one says, a skier of mass 82 kilograms is descending a 30-degree slope at constant speed. Calculate its weight, and then find the intensity of the weight's components parallel and perpendicular to the slope. Let's start with the first one. So we have a skier that is descending a 30-degree slope. This one is 30 degrees. Let's draw our nice skier. Very nice. And this one is descending the slope at constant speed. Let's calculate its weight. Its weight is very easy. We already know how to compute it. We don't need the slope. And this is W is equal to M times G, and therefore 82 kilograms times 9.81. And this one is equal to 804 times 42 newtons. Let's draw this force on the sketch. Now this is our body, our skier, and this is the direction of its weight. It's always towards the center of the earth. And this one is 804 times 42 newtons. We have to decompose this force along two lines, the one parallel to the slope and the one perpendicular to the slope, and are these ones. This is the parallel direction, and this will be the perpendicular direction. How to do so? We've seen how to find the components of a vector. We just have to project its head on those two lines. So along this direction, we'll have this one that is the weight perpendicular component, and this one, that will be the weight parallel component. And how can we compute them? Well, we know that this angle here is 30 degrees. This means that also this one will be 30 degrees. This is because this angle here is perpendicular and this one here is perpendicular. So this line and this line have the same angle that the two perpendicular lines form, that is this one. So we know this one is 30 degrees, and in order to compute the components, either we do it graphically or with an equation. And that equation is this one. W perpendicular is equal to W times the cosine of 30 degrees, while W parallel is equal to W times the sine of 30 degrees. Now, there is a way to prove that these two equations are valid, but it's too early to prove them now. We'll see them in future videos. You can compute these two equations also with your phone. It's not a big deal. You don't need expensive calculators to do so. And the two values are 696.65 newtons for the perpendicular component and 402.21 newtons for the parallel one. And these exercises are quite simple. You just have to apply the right equations, the ones that we already seen. The next one says a spring is compressed with a force of 0.1 newtons and the deformation is 0.2 centimeters. What is the elastic constant of the spring? Let's first draw a sketch. This is our wall. We can sketch the spring in this way. And let's apply the compressing force F. This one is already deformed, while the spring in its resting position is slightly longer. And this difference here is 0.2 centimeters. And this one is the delta of the Hooke's law, because the Hooke's law is F, the elastic force, is equal to minus K, the elastic constant, times delta. So we already have delta. We need to find the value of K, but how can we find the elastic force? That is the force that the spring is applying. Well, if the spring is in equilibrium in both situations, we need for the sum of all the forces acting on the spring to be zero. This means that the spring is balancing the force that we're applying with an elastic force. So let's draw this one. We have the force that we're applying and the spring force, that is the elastic force. Now the two are in equilibrium. The two forces are equal but in opposite direction. This means that if the force that we're applying is equal to 0.1 newtons, the elastic force will be equal to minus 0.1 newtons. So the elastic force is equal to minus 0.1 newtons. And if we put the two equations together, we get that minus 0.1 newtons is equal to minus K times 0.2 centimeters. And now you see why the minus is very important. We can simplify it with the minus 0.1 and we get that K is equal to 0.1 newtons over 0.2 centimeters. And this is equal to 0.5 newtons over centimeters. But if you remember, the unit of measurement of the elastic constant is Newton over meter. So we need to convert centimeters into meters. To do the conversion is quite simple. I just use this simple method. I just write centimeters, that is the one that I want to simplify. I divide by meter, and I want to make this quantity equal to 1. So I will just multiply the numerator by 100. Because you can see that 100 centimeters is equal to 1 meter. So this quantity in the square bracket is equal to 1. So the result doesn't change. Now I can simplify centimeter, and this is equal to 50 newtons over meter. And this is our solution. And let's see a last one. This one is slightly more difficult, but not too much. The exercise says, A 3 kilograms lamp is hanging from a horizontal bar linked to the ceiling by 2 identical springs to its ends. Each spring is elongated by 5 cm with respect to the resting position. Which is the spring constant of the 2 springs if the bar weight is negligible? Let's try to draw a sketch. So we have a lamp that is hanging from a bar, a horizontal bar, and this one is linked to the ceiling by means of 2 identical springs, like this. And the mass of this lamp is 3 kilograms. So we know its weight, and the weight will be the mass times g. We need to compute the elastic constant k. Let's try to simplify the sketch. We have a bar on which we have 3 forces acting on it. This is the weight, and these are the 2 elastic forces. We know that the 2 springs are identical, and also the elongation, the delta, is the same for both of them. This means that the 2 elastic forces will be the same. If the system is in equilibrium, it means that the sum of all the forces acting on it is equal to 0. So the weight plus 2 times the elastic force is equal to 0. And therefore m times g plus 2 times minus k times delta is equal to 0. So let's try to isolate the minus k, and this means that 2 times minus k times delta is equal to minus m times g. We brought m times g on the other side, and therefore we can simplify the minus, and so k is equal to m times g over 2 delta. M times g is equal to 3, because we have 3 kilograms times g, and this one is equal to 29.43 newtons. Delta, we've seen that is 5 centimeters. We need to convert it in meters, and it's 0.1 meters, and so we have that k is 29.43 newtons over 0.1 meters. That is equal to 294.3 Newton over meter. And this is it for today. Please let me know if everything was clear, if you would like to see more exercises or less, and see you next time. Bye bye.